Hi, everyone. My name's Erica. I'm a research analyst at the New York Fed. Thank you all for being here. And I'm going to be talking about DSGE.jl, using Julia for economic modeling at the Federal Reserve Bank of New York. A couple of bookkeeping items before we get started. First of all, if you want to get this presentation and follow along yourself, it's available on my GitHub, which is Moszkowski. The DSGE.jl is actually hosted by the FRBNY DSG person on GitHub. And then, so if you want to clone that, go ahead. There we go. And then the other thing is standard disclaimer, which basically says this talk reflects my experience and my coworkers' experience with Julia and with MATLAB and doesn't represent the positions of the Federal Reserve Bank of New York or the Federal Reserve System. But with that out of the way, so what are we going to talk about? DSGE is an acronym that is for a particular kind of economic model, for a kind of macroeconomic model. So I'll explain what that model is and the sort of theoretical underpinnings behind it. And then I'll talk about how DSGE.jl came to be. We had previously written up a bunch of code in MATLAB and have been using that for a while. And so how do you convince my group at the New York Fed, the DSGE team, to port our model to Julia? So I'll talk about how that happens and then the sort of the why and the performance benefits that we gain from that and all that jazz. Then I'll talk a little bit about design approaches that we take within the package. So some of these design approaches are really like Julia fundamentals, the sort of thing that Julia can give us that other programming languages can't. And then some of them are just approaches that we take to challenges that come up in economic modeling a lot. And we have one way of going about dealing with them, and so I'll talk a little bit about that. Then I'll talk a little bit about development challenges that you run into when you're using Julia in a production environment. And these probably aren't going to be that unfamiliar to anyone, but worth mentioning. And then I'll talk a little bit about ongoing and future work on DSGE.jl. So what is a DSGE model? First of all, DSGE stands for Dynamic Stochastic General Equilibrium, which is a mouthful. But what it basically is a structural model of the macroeconomy that's useful for four main kinds of things. The first one is forecasting macro variables. So, GDP growth, inflation, interest rates, all that stuff, you can forecast it with a DSGE model. The second thing is understanding what forces are behind aggregate economic outcomes. So if you want to understand, for example, we have a blog post about why interest rates are so low. And you can go ahead and read that. It's on Liberty Street Economics, but you can use a DSGE model to understand what forces are driving those kinds of outcomes. Third, we can conduct monetary policy analysis using our DSGE model. So that means, for example, we have a monetary policy rule that the central bank implements in the model, but we might want to experiment with what happens when you change that rule. And then finally, we can use the DSGE model to analyze different kinds of economic scenarios that might occur, and then figure out sort of what forces are behind those and analyze what's going on in those. And I'll note here that we use this model, our team uses this model for both research and policy work. Okay, so now let's get to the nitty-gritty. The DSGE model, in terms of like the theory and the math that's going on behind the scenes when I talk about a DSGE model, is just this. Which is a system of dynamic equations that takes this form. So here we have ST, which is a vector of states at time t. States can be things like the level of capital in the economy, for example, or the rate of inflation. And they can incorporate future expectations of states, which we just heard a lot about. So then we have epsilon t, and epsilon t is a vector of shocks that hit at time t. And they're drawn from a normal distribution with mean 0 and standard deviation q theta. Eta t is a vector of forecast errors. So under the rational expectations assumption, which is, I'm really excited that Tom just talked about the rational expectations a lot, because now you guys know what it is, which is cool. So eta t is a vector of rational expectations of forecast error under that assumption. And then theta is a vector of parameters, model parameters that describe preferences in technology. So For example, the depreciation rate of capital is a parameter. And notice that the parameters do not have a subscript t, so those are time invariant. And then finally, all these big Greek letters are just matrices of coefficients that we multiply by all these other variables. And that's our DSG model. The solution to the model is given by an algorithm called GenSys, which is due to Chris Sims. And the solution takes the form of this transition equation, equation 1. So that's a transition equation that tells us if we're at time t minus 1, and we have some vector of states, how we get to time t. And then additionally, we have a measurement equation that describes how we get from that vector of states to a bunch of values that we can actually observe and measure in the real economy. So some states could be things that are unmeasurable that we can't or don't have data about, but we can map that to a set of things that we do actually have data about using the measurement equation. And then together, these equations 1 and 2 form a state space model. So altogether, putting that all together, what is a DSG model? It's simply a mapping from the parameters theta to all of those matrices that we use to define all of those equations. And if you remember, all of those matrices depended on theta. Theta was a parameter for them. So then we need this mapping in order to compute the likelihood of observing the data that we've observed given some vector of parameters theta. So a little bit of a preview. I haven't talked about the implementation of the model yet, but DSGE.jl centers around a model object. And basically, the whole purpose of the model object is to store this mapping. We also adopt a Bayesian approach to the model. So that means that we have we think of theta as a random variable. And that means we can impose a prior on it, and of course we do. So the model object in DSG.jl also has to incorporate information about this prior. And so notice that once we know what theta is, or we have an idea of what theta is, we kind of have everything else. We can use this mapping and just figure out all of the rest of the matrices that we have and go from there. So that means theta is really our variable of interest, and we want to conduct inference about what theta is. And in particular, we want to understand what its posterior distribution looks like. So our goal, when we estimate the parameters, when we say we estimate the parameters, that means we want to sample from the posterior distribution of theta. And how do we do that? We do that using MCMC methods. Particularly, we use Metropolis Hastings. And it's really computationally intensive. This can be the most computationally intensive part of our estimation process, the estimation step of the model. And here's why. This is some pseudocode. It's Julia looking, but not exactly Julia. We go through this loop 120,000 times, just the number of times we happen to do it. And every time we draw some parameter theta, and then we solve the model using GenSys. Using that particular draw of theta. We compute the likelihood, we use that to compute the posterior, and then we do it again. And we do it a lot of times. And so this takes us maybe around 10 hours. But then once we have some idea of what the posterior distribution of our parameters looks like, all we have to do is forecast the model. And that's really easy because we have a state space model. So we can just iterate it forward as many times as we want. And then we can draw values of epsilon, the shocks, and apply those to perturb the system. OK, so that gets me to DSG.jl, which is our implementation of the DSG model in Julia. And DSG.jl is a package that is used to solve and estimate DSGE models. So basically, the idea behind DSG.jl is if you're an economic researcher and you want to use a DSGE model, all you have to do is specify your own model. And then we'll take care of the rest of it for you. We have all the methods that you need to solve and estimate and eventually forecast your DSGE model. So there are 4 main sections. The first section is data preparation. So you need to feed some data into your DSGE model, and you might not get it in exactly the right kind of transformation that you want to be able to put it into your model. So we have a step that involves pulling data using freddata.jl, which was written by my colleague Micah Smith. You can pull the data directly in Julia natively from Fred and then transform it appropriately for input into your model. Then there's the estimation step, which estimates the posterior distribution of theta. And then you can forecast the model, the forecast step, and then finally plot everything so that you have nice visualizations of what all your forecasts look like. And then there are additional features that we'll work on once we get all of that done. So using DSGE looks something like this. First, using DSGE, and then most of the user work comes in implementing the model object. So the second line, m equals model 990, means I'm constructing an instance of model 990, which is the sort of example model that we've provided in the package. If this is the part that if you were a user of DSGE.jl, you would define your own model type and instantiate it here. And then you can add change some settings. So you can change, for example, the date of the vintage of data that you want to use to estimate your model on, which is what we're doing here. Then you load your data, and then you can just estimate the model. Just call estimate, and we take care of all the rest of the implementation for you. And then if you wanted to produce some tables of moments and stuff, you could do that. That's as much as we have implemented now. We're currently working on the forecasting and the plotting, so all of this works, and everything else is sort of still to come. But in terms of functions that are usable out of DSGE.jl, we have a bunch of functions that are actually model agnostic, so you could use them even if you weren't using a DSGE model. If you wanted to use, for example, our implementation of Genesis, or our implementation of an optimization algorithm called CS-Minwell, or if you wanted to use our implementation of the Kalman filter, you could do that out of the box. OK, so some people might be wondering how you convince a team at the New York Fed that they should use Julia, because they have a perfectly functioning model in MATLAB, and it seems like a lot of work to port it. So why would you do that? Well, so here's a little bit of the background and the story. So DSGE at the New York Fed started around 10 years ago. And in September of 2014, we released our code publicly on Liberty Street Economics, which is the New York Fed's research blog. And so sort of this code was out there, but it was in MATLAB. And then in the spring of 2015, which is actually a couple of months before I started at the Fed, QuantEcon approached us and said, hey, you should really think about porting your DSGE model to Julia or to Python. You should make it in a truly free and open source language. And for us, this was actually a really great opportunity, because we are running up in our MATLAB code, we're running up against what it was actually feasible to do in terms of time. So we were at a point where we really needed to improve our performance if we were going to experiment with things like nonlinear models. I should say our model right now is completely log linearized, or almost completely log linearized. And so doing anything that involves nonlinear estimation is a significant challenge, and not something that we were going to be able to do in MATLAB. We were also excited about the opportunity to port the code, because we've been dealing with this code for many, many years. There have been many, many generations of RAs that have dealt with our MATLAB code base. It's getting kind of ugly, so this gave us a chance to redesign the code base from a bottom up. And this was truly a chance for us to make our code free for any researcher who might be interested in working on DSGE models. You don't need to have a MATLAB license, which is, for us, very exciting. So then in December of 2015, we released the estimation step of DSGE.jl. And actually, earlier this week, we released the data step. So if you wanted to check that out, you can go do that. But why did we go with Julia? So QuantEcon sort of does stuff in both Python and Julia, so why did we go with Julia? And to be honest, at the beginning, we didn't have great reasons. We got a little bit of a push from QuantEcon, you should really use Julia, it's really a good choice. And coming from a MATLAB background, it's a little bit easier to read Julia than it is to read MATLAB. But hindsight, fortunately, is 20/20. So with some reflection, a number of Julia features, and just some of them here, really lend themselves to what we think is a really good implementation of a DSGE model. So for example, the central type system in Julia is something that allows us to express and organize and simplify our code base and express things in a very intuitive way. Dispatch allows us to write more general code so we can handle more kinds of models more easily. And then we can rely on the compiler to boost our performance. And that'll give us the flexibility to do things like estimating nonlinear models like I talked about a little bit before. So now I'll also show a couple of performance stats that are motivating in terms of like the kinds of benefits that we've been able to see from moving to Julia. But keep in mind, DSGE.jl is not exactly a direct port from MATLAB to Julia, so they're not completely comparable. On the other hand, I think these are helpful a little bit. So moving to Julia helped us reduce the lines of code in our estimation step by about half, which means code maintenance is a lot easier. And then these are sort of the main and most important functions that we have implemented. And the top block are ones that are pretty much direct ports. And as you can see, we get performance improvements on all of them. There are probably ways we could make some of them even better, but notice particularly that the solve function is like 11 times faster than it was in MATLAB, which is great for us because that's one of the things that we have to do 120,000 times. So that's a lot of the reason why Metropolis Hastings, our sampling algorithm, is 9 times faster in Julia than it is in MATLAB. OK, so now I'm going to talk a little bit about the design of DSGE.jl and how we use Julia in really useful ways for economic modeling. So in Julia, it's really natural to take a type approach to kind of anything, and so that means you can take a type-oriented approach to a DSG model. So we think of the entire model as a type, but we can actually have types kind of all the way down to express any kind of intuitive economic idea. And they're useful because you can encapsulate all information about that economic object in a single data structure. So you know where everything about it is, and it's easy to see and to understand and to organize, and it makes it really easy to call any function on that object because any function that you give that object to will have access to everything that's stored inside of it. It also makes it really easy to do dispatch on different model types and things like that, and that sort of dispatch really supports our economic intuition. I'll give an example of that in a minute. And so then we have a lot of different types in DSGE.jl, but one of them is the model itself. Another one is the parameters. And another one is sort of computational settings, which I'll talk about in a little bit. So parameter types is our implementation of the theta object. And so remember that theta is not just a value, right? We talked about the fact that it has a prior. It also has a bunch of other things associated with it. So it has a name or a key. It has a value, which is the value that it takes on in any particular draw. It also might have bounds. So we might have some parameter that we need to bound between 0 and 1, because say that parameter represents a fraction, like a percentage of something, then it needs to be between 0 and 1. And we might decide that we want to fix that parameter or calibrate it to something certain, some particular value. It means we don't want to estimate it, so we can do that. And then we can print it nicely and that sort of thing. So here we have a parameter alpha that we construct to have some value, 0.1596 in this case. We bound it to pretty much be between 0 and 1. And we say that it has a normal prior that's centered at 0.3 with some standard deviation 0.05. We want to estimate it, and we can print it out. And because we sort of think about being able to add things to parameters, it's really natural to think about having alpha plus 1. So we can do that. We just overload the plus sign. But we also, that's not enough for us. We also want to have 1 plus alpha. And so we can do that in Julia, no problem. And this is really easy, but it's not so easy in other languages. So the ease with which we can do this in Julia is fairly unique. And why do we care about this sort of thing? Why do we want to do that? Well, because when the user is defining their model type and they're implementing it, that's the only thing that we really ask them to do. They're going to do a lot of things that look like this, right? We want it to be easy to go between the math and the code, and we don't want you to have to go back and forth between your code name for a particular variable and your math name for a particular variable. We want those to be the same. So it's really easy to do that in Julia. And this is just a very, very slight simplification of what the actual syntax would look like. So it pretty much looks like this. The next thing I'll talk about a little bit is computational settings. So what is a computational setting in sort of this terminology that I'm using? A computational setting is something that doesn't necessarily have economic intuition. It's not part of the economic story that we tell when we describe a model, but it's something that we need in order to be able to solve it, in order to be able to implement it. So for example, can I read in a pre-optimized parameter mode? Or do I have to actually estimate the whole thing, which will take me a bunch of time? How many times do I want to go through that loop in Metropolis Hastings? I can change that. What vintage of data do I want to use? These are all things like, these are all kinds of settings that we could have kind of all over the place, and we'd really like to organize them, keep them in one place, and be able to deal with them all in a sort of similar way. And so we implement a settings type, which basically is a wrapper for the value, but it's a parametric type. And then it has a name, it has the value of the setting, it has a description in it, and then it has these two fields, print and code, which I'll talk about in a minute, but they help us with dealing with I/O, naming files and stuff. And then we store a dictionary of all of these within the model object. So we don't have to go hunting through the source code to find out the value of a setting, to change it. It's really easy to change it. You can change it from the REPL, you can change it from a script, you can do whatever you want. So then we use settings also to solve a big problem that we run into in terms of creating a lot of output files. When you're using a model or for production purposes, like we do with the DSGE model, we have a lot of versions of the model, and then we have a lot of vintages of data that we estimate it for and forecast for, and then we change settings a lot. And so we just make a bunch of files, and we want to be able to easily identify which files correspond to which time we ran the model with what settings. And so every time we print something to a file, we want to be able to name that file appropriately, and we use settings to do this. So the print and code fields help us do that. So print, oops. Yeah. OK. So the way that that sort of looks is that when we construct the model object in the constructor, we make this dictionary of settings. And then we might want to change some of the values of the settings later on, either in the code or from the REPL or whatever. But then whenever you're printing to a file, we simply go through the dictionary of settings. And for all of the settings for which print is true, we concatenate them all together with their code and their value, separate them with underscores, and then add that as a suffix to the end of the file string. And so this is like pretty boring stuff, but it's actually super useful. And this is the kind of thing that people who are using Julia for production work or for modeling run into all the time. And so it's something that we sort of felt like was worth mentioning. There are probably ways to do this better. If other people have other ideas, let us know. But we think it works pretty well for our purposes. So now I'm going to talk a little bit about development challenges of or using Julia in a production environment, which I think is fairly different than using Julia in an academic or research environment, although we do use the model for research purposes too. One plug for interfaces. I know that might not be something that goes into Julia 0.1 or 1.0, but for us, there's something that would be really useful, because the only thing that we ask users of DSGE.jl to do if they want to implement their own model is, well, to implement their own model. And it would be really useful for there to be some sort of language construct to sort of be able to tell people, hey, it'd be great if your model, your model has to have these specifications. It needs to have this particular field. These particular conditions need to be met. And right now, the only thing that stands between a user completely using everything wrong is a README in our repository. So we think it's pretty good, but it's not actually part of the language. We wrote it ourselves. So that's our plug for interfaces. It would be really nice to have a debugger that works properly. And so I'm really excited for moving to 0.5 to use Gallium. Right now, we need the stability of 0.4. So we're not there yet, but we're excited to have that. Another interesting challenge is sort of the maturing package ecosystem in Julia is interesting. So when we set out to implement the Kalman filter, for example, we looked around and we thought, are there any other implementations that we could use? And we checked out a bunch of them, and none of them really seemed to be right for us. So what did we do? We wrote our own Kalman filter. So maybe there were 4 before, and now there are 5. So I mean, maybe some way to deal with this could be useful. And then finally, Stack Overflow activity about Julia is pretty sparse. So that means convincing other people to use Julia for their models is challenging. It's been an investment for those of us who've been writing DSGE.jl to really learn Julia, to dive into GitHub issues that have been open for X years, and that sort of thing. So this is the sort of thing that once Julia is more of a stable language that has more sort of convenient stuff like questions being asked and answered on Stack Overflow, I think you'll see a lot more people starting to use Julia for their modeling. That's just my opinion there. And then ongoing and future work, we are currently working on the forecasting step of the model and on the plotting step of the model. So we hope to have those out at some point pretty soon, hopefully. And then after we get that implemented and we sort of have all the functionality that our MATLAB code base had, ported properly over to Julia, we'll start experimenting with new techniques. So one of those is the nonlinear estimation model, or nonlinear estimation and solution methods, which is sort of one of those big things that we're really excited about. And then we might want to try using different optimization algorithms. We use CS Minwell, which is a bit old, so maybe there are better options. And new estimation methods. So right now we use Metropolis Hastings, but we might want to move to sequential Monte Carlo, and that's something we're thinking about and kind of working on at the moment. But we're pretty sure that there are ways to do just about anything in DSGE.jl a little bit better, or a lot better, as the case may be. So we really welcome pull requests, thoughts, suggestions from any of you. So feel free to contact us or find us and let us know what you think. And then just some quick acknowledgements to my team at the New York Fed. Marco Del Negro and Mark Giannoni are our economists, and then we have research analysts Sarah Shahnagi and Micah Smith, who's actually here. And we had an intern last summer who really got all of this started, Pearl Lee, and she's going to be joining us next week full time, which is awesome. And then a big thank you to our QuantEcon collaborators and the people who helped us A, learn Julia, and B, make our code actually like decent and fast and stuff. So that's Zach Krenka, Spencer Lyon, Pablo Winant, and John Sachersky. So basically what we covered, what a DSG model is, DSGE.jl and how it's implemented, design approaches that we took to the model, development challenges that we ran into, and the future directions of DSGE.jl. So thanks a lot, and if you have any questions, I'd be happy to take them.